This is stock price prediction using machine learning techniques. So the aim of our team is to build a data pipeline with engineered indicators and to train an LSTM. And the goal is to benchmark against an ARIMA and to forecast the price movement for the Magnificent Seven stocks using price history, volume, and external data market signals. And the overall goal is to outperform the traditional buy and hold strategies. So our data set comprises of price and volume histories from multiple timescales for the Magnificent Seven stocks. And these timescales include 1, 5, 15, 30, 60, and daily bars. And our dataset also contains other engineered statistics and indicators such as the moving averages, the RSI, the MACD, and the Bollinger Bands, and more. So based on midterm feedback to evaluate our model more effectively, we adopted the F1 score as our primary metrics. And for the data collection pipeline, we primarily relies on Yahoo Finance, which is an open source Python library that provides an interface to Yahoo Finance API, which lets you easily retrieve historical price data, fundamentals, and real-time quotes, and other things like the tickers, download market search, and more indicators.
Hi, I'm responsible for the second part, data processing. After collecting raw stock price data from Yahoo Finance, I built a Python pipeline to clean and structure it for both statistical and deep learning models, ARIMA and LSTM. We gather price data for each stock at multiple time intervals, including short-term 1 minute to daily, so we can capture both short-term movements and long-term trends. The data is stored in CSV format, and we prepare two types of outputs depending on the model. ARIMA used the raw closing price directly. For STM, we apply technical feature engineering and convert data into normalized MPZ files using sliding windows, making it compact, structured, and ready for training. All outputs follow a consistent folder structure by stock and timeframe, allowing models to load the data seamlessly. Once the data is cleaned and organized, we enhance it with technical indicators like RSI, MACD, Bollinger Bands, ATR, and moving averages. These features help the model detect momentum, trend shifts, and volatility patterns not visible in raw prices. For example, here's how some of those indicators look in Apple's daily chart. You can see the price with Bollinger Bands and moving averages, the trading volume below, and MACD at the bottom, showing the trend strength and reversals. These engineered features, combined with sliding window formatting, enable the LSTM to learn temporal patterns more effectively. In short, this pipeline turns raw price history into rich, model-ready datasets. With these features in place, LSTM constantly outperform ARIMA by 5 to 8 F1 points across most stocks, showing clear improvements over both traditional models and simple buy and hold strategies.
We established a performance benchmark. We began with a traditional time series forecasting model ARIMA. While ARIMA is well suited for modeling near linear trends, in our cases, it consistently produced flat or smooth prediction lines, indicating limited responsiveness to short-term fluctuation on stocks. Despite this, the ARIMA baseline yields quite reasonable results, particularly in binary classification tasks on longer timescale datasets. For example, on the dataset of Amazon, it achieved F1 score nearly 0.7. Overall, while ARIMA serves as a solid baseline for tendency prediction, its performance is limited by its assumption of linearity. And in the next image, we can see another example of our results. You can see ARIMA prediction line is always monotonous. So we decided to develop another model LSTM to improve our performance.
So our primary LSTM model consists of these key components. So first, the NN.LSTM layer. This is the heart of the model. We configured it with an input size matching our features with open, high, low, close, and volume. The hidden size set to 64 in our configuration file defines the dimensionality of the internal memory cells. We stack two LSTM layers for potentially learning more complex representations. I also set in the config. A dropout value of 0.1 was applied between these layers to mitigating overfitting. We also specify a batch first equals to true, so the input tensor have the batch dimension first, which is convenient. And second, the NN linear layer. This is the standard fully connected layer that takes the final output from the LSTM sequence and maps it down to our desired output size, which is 1. For predicting a single value like MACD line, now let's trace how data flows through the model during the forward pass. For each input batch, we first initialize the hidden state and the cell state tensor with zeros. These provides the initial context to the LSTM layer. Then, the input sequence along with these initial states are fed into the LSTM layer. The LSTM processes the sequence step by step, updating its internal states. The LSTM layer outputs the hidden state for every time step. Since we need a single prediction based on the entire input sequence, we selected the output from the very last time step. Finally, it's the last hidden state vector, representing the earned features from the sequence, is passed through our fully connected layer to produce the final prediction value. So this is what we got when we using our LSTM model for Amazon stock price with the F1 score of 0.74. So this is the we using LSTM on the Microsoft stock. This is the before we add a drop-off layer before the output in our LSTM model design. And after is we have F1 score of 0.58. And this is the NVIDIA before we implement that feature. And this is the NVIDIA after we implement that feature with the F1 score of 0.7372. And the last one is Google. And this is we get the F1 score of 0.62. So the last is our baseline model ARIMA and the LSTM model comparison. So we have Amazon when we using ARIMA baseline model with on Amazon, we get an F1 score of 0.68. And when we using LSTM on the Amazon, we get an F1 score of 0.74. And NVIDIA, when we're using ARIMA, we get a 0.71. And the NVIDIA, after we implement the LSTM model, we get a F1 score of 0.73. I think that's a pretty decent improvement. That's all. Thank you, guys.